In this lecture, we will see stress-strain relation. So in earlier lectures, we have understood the concept of stresses and strains. We understood how the stress feels, okay, and what is the relation between traction and stress. And then we have seen strain measures. So we have quantified the strain. We have derived various strain components and different types of strains. So once from displacement is known, we know how to calculate strain. But now we will see like how to calculate the stress from strain. So let me recap the FEA steps. Okay. So earlier we have discussed FEA steps. First we write the element level stiffness matrix. Then we perform assembly of elements and we get a global system of equation. Then we apply loads and boundary condition, and next step we solve the problem. That means we find the unknowns, find unknown displacements. Then with 1D element in 1D space, in chapter 1 we have tried to understand the calculation, and in that we have shown like how to calculate strain and stress. So from displacements we can calculate strains first, okay, and we have seen in concept of strains and different strain measures like how to calculate strains from displacement gradient. Then once strains are known, we can calculate stress components. So let's see the relation between stresses and strains, okay, so that we can compute stresses. So stress strain relation sigma epsilon is it describes a material behavior. It is a material property, and can for 1D case we know, for 1D we know the stress strain relation sigma is equal to E epsilon. And for 3D, can we write something like this? Sigma ij is equal to E epsilon ij. So we cannot write something like this, okay, because it is not so straightforward. We know it is not due to this. No, this is not valid due to Poisson's ratio effect. So let's see the strain components, I mean, in terms of stresses. So epsilon 1 is equal to sigma 1 by E. So this we know, okay, and uh, there is a effect of Poisson's ratio nu. Okay, so Poisson's ratio defines the change in strain due to the stress in other directions. Okay, so stresses from sigma 22 and sigma 33, those also produce strain in other direction, that is 1 1. Okay, and that is called Poisson's ratio, and that is the reason we can write epsilon 1 1 as sigma 1 1 by E minus 1 by E Poisson's ratio, and sigma 22 plus sigma 33. And just rearranging the terms, we can write epsilon 1 1 is equal to 1 by E sigma 1 1 minus nu sigma 22 plus sigma 33. Similarly, we can write strain epsilon 22 epsilon 33. Okay. Epsilon 1 2 strain, okay, strain matrix, the shear strain component epsilon 1 2, which is equal to shear strain divided by 2 gamma 1 2 by 2, and gamma 1 2 we can say it is sigma 1 2 by G, stress divided by shear modulus. Okay, shear stress divided by shear modulus is shear strain. So epsilon 1 2 is equal to sigma 1 2 by 2G. Similarly, epsilon 2 3 and epsilon 1 3. And there is a relation between G and E, Young's modulus and or elastic modulus and shear modulus, which is given as this expression. Okay. So we can substitute G in form of E here. Okay, and what we get is no epsilon vector in form of stress vector. Okay, and can just no, from this what we can get is all six component of stress strains in form of six component of stresses. Okay, in between we will have matrix which is 6 by 6. Okay? This is 6 by 1, 6 by 6 and 6 by 1. So we can rearrange these terms. I mean stress vector we can bring it on left side and strain vector on the right side. So rearranging them, okay, we can get the stress strain relationship for 3D. Okay, and the relationship is given in this form. Note that stress and strain are matrix. Okay, we always till now we have referred stress matrix and strain matrix, or stress tensor or strain tensor. But for computer or computations in computer, the vector representation of stresses and vector representation of strain components are more convenient. Okay, and that is the reason we are representing it in form of vector. Okay, so this is 6 by 1. We have six component of stresses and six component of strains, which is related by this matrix 6 by 6, and this is called D matrix. Okay, so in a non-linear lecture we will see, or not even till non-linear, in Jacobian and integration points, when we are talking about this concept, we will see this D matrix. Okay? D matrix is nothing but it is stress, it is called stress strain relationship matrix. So this is going to be very useful in upcoming lectures and chapters. And this is for 3D. So for 1D we have already seen sigma is equal to E epsilon, because there is only one stress component and there is only one strain component. Similarly for 3D, we will have three stress components. Okay? Sigma 1 1, sigma 2 2, sigma 1 2, which is related to strain vector epsilon 1 1, 2 2, 3 3, sorry 1 2. So this is for 2D, okay, in which we have three stress components and three strain components, and therefore D, which is stress strain relationship matrix, is 3 by 3. Okay, and for 3D we have already seen it is 6 by 6. Now let's say a very special case of 2D, that is plane stress. Okay. So plane stress is the condition. Okay, I mean it is applicable to thin plate like structures. Okay, for example rotating wheel. Okay. Thin plate like structures means the thickness direction or thickness dimension is very negligible or very small compared to other two dimensions or other two in plane dimensions. So in such cases, it is we can say the plane stress condition is valid. Okay, and another condition is that for this kind of structures, forces act in a plane. Okay, so there is no force okay, in z direction. Okay, it is not it doesn't act any z direction force. So only in plane directions or in plane forces are existing. Okay, and we can understand this like no, when the thickness is very small, negligible. Okay, why it no, we can say like sigma zz, that means the thickness direction stress is zero. So this is sigma zz or sigma 33 is equal to zero, is called plane stress condition. So we can understand this from our continuum mechanics. Okay, the stress concepts. Okay, we have infinitesimal volume element or Q. Check, this is X, Y, and Z. Okay, so we know sigma ZZ acts on this plane, okay, this plane, and similarly it also acts in opposite phase. Okay, here sigma ZZ, and that's how they are. We can say it is in equilibrium. Now, for stresses, okay, I mean the stresses always act on two opposite planes. Okay, if we talk about sigma z0 or sigma 33, uh, they are acting on this it is acting on this phase and opposite phase in opposite direction. And if in that case only it will produce the stretch, right? If it is acting only in one direction, it cannot stretch. Like under the influence of sigma 33, there cannot be stretch if there is only one direction stress. So always there are two opposite direction. Normal stresses are acting on two opposite directions and two opposite planes. And from this concept, we can understand that if this thickness is very negligible, this thickness very negligible, okay, so there is no room that we can define two planes. Okay, and in that case there is no stress develops in a thickness direction. So from this continuum mechanics we can understand that easily, that sigma 33 is equal to 0 for thin plate like structures. Okay, because there is no room for resisting the force in thickness direction. Okay, and given sigma 33 equal to 0, okay, we can also say in plane 3, okay, their shear stresses are also 0 because plane 3 or uh, plane 3 is very small, there is no room for shear components as well. So given this condition, when we put substitute those conditions here, okay, we can write the stress strain relation, we can derive the stress strain relation for plane stress. Okay, which looks something like this. Okay, where the three stress components are related to three strain components using D matrix 3 by 3. So we have sigma 1 1, sigma 2 2, and shear stress in plane, okay, in that plane 1 2. So let's see now plane strain condition. We have seen plane stress. Now plane strain is another extreme condition. In plane stress, we have seen the thickness is very negligible compared to two dimensions, whereas plane stress is another extreme where we say the thickness direction is very large compared to other two in plane dimensions. This is another extreme case. So for example, thick cylinders, okay, uh, and in this also the forces act in a plane. This is the condition. So when we say okay, this thickness direction is very large. Okay, so thickness direction strain epsilon 33, which is equal to, let's say, delta t by t0. Okay, change in thickness dimension divided by original thickness. So when we say delta t by t0 is equal, it becomes 0, because we are assuming that the thickness dimension, that t0 is very large. This is very large. In that case, the change in thickness, okay, will be very small compared to t0, and that is the reason we can say epsilon 33 is 0. So given this condition, we can use here, okay, and we can simplify the stress strain relation, stress strain relations in a, we can simplify in this manner, and we get something like this. Okay, sigma 11, sigma 22, and sigma 12. These are all in 1-2 plane stress components, two normal stress components and one shear stress component, which is related to uh, two normal strains and one shear strain. So this is our D matrix for plane strain. Now you understand that, okay, the D matrix, this I will repeat again in our FEA concepts in future chapters. The D matrix is a stress strain relationship matrix, and it depends only on dimensionality of problem. Okay, if it is a 1D case, it is simply E. If it is a 2D case, it is 3 by 3, and if it is a 3D case, it is 6 by 6. So we understood stress strain relationship for three cases, 3D, plane stress and plane strain. Now I just want to explain one more concept, uh, free surface. Okay, let's take no, there is a coordinate system here, x, y, z, and let's say there is a 3D body. You can imagine this is a 3D structure or component. Okay, the thickness is very large. I have, let me delete this. This is, you can imagine this is a 3D component. Okay, now for 3D component, always the stress, okay, stress in normal to the surface is always equal to 0. Okay, this concept is very similar to our plane stress. Okay, we are saying that thickness is very negligible, that there is no room for a stress development. That means there is no opposing planes which resist the deformation. So in this case also, in free surface also, the surface is present, but to produce the stress in surface normal direction, there is no another surface which can resist this deformation. Okay, and therefore the sigma n, the stress component normal to the surface, is always equal to 0. Now note that though in FEA you will see sigma 11, sigma 22, and sigma 33. Okay, all are non-zero in your 3D FEA structure. So though just remember that I have said the stress which is normal to the surface is 0. Okay, but that surface can be oriented in any direction, right? It is not that it is always oriented in z direction or y direction, and therefore on surface you will see all three stress components. Okay, but the normal, when we resolve it into normal, no, if we take normal component, create local coordinate system where one of the axis is normal to the surface, and then if we report the stress, it will be always 0. Now there are cases, okay, where the there are normal stress sorry stresses normal to the surface are not zero. Okay. It is not called free surface. Okay, but there are some cases, for example contact. Okay, when two components are contacting, okay, though this is a free surface, okay, this is a free surface, but there is resistance from the opposite side. Okay, and the stress component here in the contact region is not equal to zero. I mean, we cannot say it is a free surface because the surface is no more free in the contact. Similarly, when we apply the pressure, or when we apply boundary condition, like, okay, for example, say we apply the pressure in this much region. Okay, here also there is a resisting force, so here also we get normal stresses. Okay, stress is normal to the surface. Okay, so here also it is not zero. Similarly, if we arrest this boundary, here also we get no resistance to the stress normal to the surface. So in these cases, this is just one observation in FEA post processing. And similarly, we can also say that, okay, this surface on free surface, always, as I said, this is a zero. Okay, so there are only, let's check this surface. Okay, okay. There are always two stress components in plane. Okay, it can be in any compressive or tensile, anything, just for understanding purpose. Okay, let me draw it here properly. Let's say this is compressive and this is tensile. So there are always two stress components, okay, available on the surface. And normal to the surface is, as I said, is zero, and therefore this is also called biaxial stress state. And these concepts you will hear in fatigue analysis. Okay. Anyways, so this particular slide is for additional information, and I hope you find this helpful or useful.